Okay, next up, let's do an indeterminate example. So I've got this circular shaft here, and it has been mounted between these two walls at A and B. And not only that, but it also has a hole drilled in it from one side. So from the B side, it's got a cavity. That cavity is 120 millimeters long and 16 millimeters in diameter, whereas the shaft itself is 250 long and 22 millimeters in diameter. It's steel, and we are applying a 120 Newton meter torque to that shaft at the center. So basically at the point where the cavity ends. So we're looking to find out what the torque exerted on the shaft by each support is, so what the reactions are, shear stress induced, and the angle twist at the center. So again, equilibrium is not enough to figure out what these reactions are. We'd have two unknowns and one equation, so yeah, we're a bit out of luck if all we did was the statics portion of 231. But fortunately, we've learned more. So what we do know is that the total twist over the two halves must be the same. That essentially when we apply this load, this portion here is going to start twisting this way, and then we're going to get a certain amount of twist back. So like a line that was initially straight right here is going to end up looking something like this instead. And we know that the amount of that needs to be the same for this to be continuous. So we can figure out what sort of reactions would cause that to occur. So we got our compatibility condition that the total twist over the two halves needs to be the same, and we just break it up into two segments. So I took my free body diagram here and broke it up into two separate free body diagrams. So we got the solid rod section from A to C, and it has the reaction at A, and then I'm going to call it T1 for now, and then we got the segment from C to B. Again, it's got the reaction at B, and it's got T2. So we know that basically T1 and T2, that's combined some portion of the point load is going to go this way, and some portion is going to kind of go this way. Is kind of the way it's going to work. But those two things combined needs to be equal to the original load. And then, of course, the magnitude of those, T1 needs to be equal to TA, otherwise this thing's spinning out of control. Same thing on this side. T2 needs to be equal to TB, or else this thing's spinning out of control. So essentially just, TA plus TB is equal to 120 Newton meters. So you will recall the sign convention for the angle of twist. So basically if we're going down the x-axis, anything that causes, if we're looking down the x-axis, anything that causes like a line that initially looked like this to go like this is a positive twist. And again, that's because if we were fixing this thing on this end and applying a positive moment about the x-axis, it will cause a positive twist. So our sign conventions match what we expect to see for both torque and angle of twist, in the same manner that the sign convention for tension matches the sign convention for shear strain. For axial strain, and sign convention for shear stratus matches the sign convention for shear strain. Positive causes positive, negative causes negative. So yeah, this portion here is going to be having a positive twist, and the segment CB will have a negative twist. And then adding together, those two things need to be equal to 0. So that is equal to that. We got the formulas here for how much something twists over its length. So the torque times its length divided by J times G. And then all that equals 0, since that's our compatibility condition. So since we got this equation here that's equal to 0, and we know that the lengths are the same, 125, 125, we can just divide by 125 millimeters and cancel those out. We can multiply by G to cancel those out. And then we're left with TA over JAC minus TB over JCB is equal to 0. And then we'll need to know what the J's are. So again, the J for a circular cross-section, that's just equal to pi over 2 times the radius to the fourth. So for AC, pi over 2 times 11 millimeters to the fourth gives us this. And then for the tube portion, it's basically the same thing, except we're subtracting the J for the negative space here. So if this is positive J is based upon this, and then we subtract the portion based upon here. So we're working with pi over 2 times the outside radius to the fourth minus the inside radius to the fourth. So pi over 2 times bracket 11 millimeters to the fourth minus 8 millimeters to the fourth gives us this value here. So we can plug that into the equation that we had here, and we can fairly easily solve for TA in terms of TB. So TA needs to be 1.388 times TB, so it's a bit bigger. And that's not surprising, because basically what we're saying is that if we're twisting these things, if these things need to twist to the same degree, and this thing has a hole in it, it's going to twist easier. So in order to twist to the same angle, we need to twist harder on this section. So, and then we're going back. We can go back to this equation here. The sum of those two needs to be equal to 120 Newton meters. So TA plus TB, plug in the 1.388 TB into here. We got 120 Newton meters is equal to 2.388 TB, which means we can solve for TB. It's 50.25 Newton meters, and TA is 69.75 Newton meters. So we got the reactions. I also want to find out what the twist is at the center. So basically, it's going to be this. We'll calculate the same things working from either side. So I'm just going to figure out what it is based upon the section from AC. Got our steel. We're working steel, so the modulus of elasticity there is 75 gigapascals. And then again, got our formula here. Angle of twist is torque times the length divided by J times G. Plug in those numbers. And then, of course, we got a bit of a mess with units, so I always like to resolve, no, you need to resolve exactly how the units cancel out you need to do so properly. Don't screw up how canceling out your units. So I got Newton meters times a millimeter divided by millimeters to the fourth GPA. What's that? So Newton meters times a millimeter divided by millimeters to the fourth GPA. So I crossed out one of the millimeters, and then subbed in GPA for kilonewtons per millimeter squared, because of course a megapascal is a Newton per millimeter squared, so kilonewton per millimeter squared is a GPA. So subbed in that and then canceled out the 2 more of the millimeters on this term. Leaves us just a 1. So we got Newton meters per millimeter. And then, Newton meters per millimeter kilonewton. So subbed in 1,000 newtons for the kilonewton, crossed out the newtons. That left us with meters per 100 millimeters. Well, we know that 1 meter meters per 1,000 millimeters. Well, we know that a meter is 1,000 millimeters, so 1,000 millimeters divided by 1,000 millimeters cancels out. So, conveniently, our Newton meters millimeter per millimeter to the fourth GPA cancels out to radians, which is exactly what we're going for. Or it cancels out to a dimensionless ratio, which, given this equation, is a radian. So we are left with 4.06 times 10 to the 3 radians, or if you wanted to put it in terms of degrees, it's 0.3 degrees. So not a massive amount of rotation there. And then we can go to our stress. So we know that the stress is torque times the distance from the center divided by J. So we know what our we know that our torque is 69.75 Newton meters in the section C, AC here, 69.7. And then I just subbed in 1,000 millimeters per meter, so I could cancel out the meters and put things in terms of millimeters, because I got a bunch of millimeters down here and I didn't want to worry about it. And then 11 millimeters here as well. So again, these canceled out. This cancels out one of them. This cancels out another one of them. So we're left with, in terms of units, left with newtons per millimeter squared, and then multiplied, or obviously the numbers multiplied together. So that ends up giving us 33.4 newtons per millimeter squared, or 33.4 MPa, megapascals. So that's in this section here. And then we go to the other section, CB. Different value for our torque, different value for our J, ends up giving us the same value, which I guess